Archiving started.
All right, welcome to Women in Science and Engineering. My name is Dr. Ashley Spring, and I teach biology here at the Melbourne campus. And my co-program chair is Dr. Mary Roslynowski, who is our Associate Provost here at the Melbourne campus. And I today would like to introduce you to our guest speaker, the first speaker of the spring 2014 semester here at ESSC is Lindsay Fletcher, who is visiting us from ENSCO. I'd like to tell you a little bit more about the Women in Science and Engineering program here at ESSC. Our goal is to help promote underrepresented groups in science, technology, engineering, and math, and for those pursuing careers in these fields. WiSE is open to all students. Some of the things that we do are seminar series like you're attending today with guest experts, workshops on careers and resume building, of which we have one coming up on April 10th, visiting graduate schools and other schools, networking for future schools and employment, local excursions. We have a field trip coming up on April 3rd as well. Career mentoring. All of our speakers, their information is posted on our website, www.easternflorida.edu/WiSE, so you can contact them with questions about careers and so on that you're interested in, as well as undergraduate research. If you're interested in undergraduate research, contact myself, and we can get you started in research as an undergrad here at the ESSC before you head out into the world. Get that on your resume and experience under your belt. Our speaker today is Lindsay Fletcher, a chemical engineer from ENSCO. Next month, February 18th, we have Erica Cabrero from Zell Technologies on systems engineering. She also formerly worked for the CIA and for some of our telescopes. On March 18th is Eileen Corelli, Senior Scientist for ENSCO, who is now a member of the Math Department here at ESSC. On April 15th is Jody Palmer, who is the head of the oyster restoration with the Brevard Zoo. If you have not received an email recently from the Brevard Zoo or Nashville County Resources or us about all of the upcoming oyster research, you will be soon. It is a big event that is Brevard County and more, extending into Indian River County and greater parts of Florida. Coming up on April 3rd, we have a field trip to UCF, where we are going to pile us into a van, head over to UCF around lunchtime, returning around 5 o'clock or so, to visit their showcase in undergraduate research. And then there's a workshop on April 10th with Luke Robertson, who's president and founder of Vaulted Technologies, talking about finding your career in STEM, science, technology, engineering, and math, as well as how to build a resume, a STEM resume, which is different from resumes in all the other professions. If you have any questions, ask me or visit www.easternflorida.edu/WiSE. And without further ado, I would like to introduce Lindsay Fletcher. Thank you.
Hi, good afternoon. As Dr. Spring said, my name is Lindsay Fletcher. I am a chemical engineer at ENSCO. I am born and raised in Michigan. I lived in Florida for the last 7-8 years, so I do consider myself a Floridian, besides the fact that I love it much more than Florida, much more than Michigan. I have a bachelor's in chemical engineering from Michigan State, a master's in chemical engineering from Florida Tech, and as I said, I am currently working as a chemical engineer at ENSCO, a small private engineering firm right here in Melbourne, right on some road, actually. So before I delve into what my job entails at ENSCO, I would like to share my path with you. So, my path started back when I was 11 years old, and I can't believe this, My mom would be very proud right now, but it started with a green sheet of paper, a bank ledger. My mom handed this to me, and I was supposed to record all of my sources of income and outcome. This is at 11 years old, babysitting. I was making, as you can see, huge amounts of money, and I was allowed to spend half of everything that I made. I would record if I made $10, I could put half into savings, and I was able to spend half. And that half for savings was a savings for college. I was 11 years old, did not know what college was, but this was so grateful when I did learn what college was that I had this fund for college. I could look into my envelope to see how much money I had. I would save up hundreds of dollars before I would deposit it into the bank and see I had hundreds of dollars. But look at that green sheet of paper and see, wow, I don't have all of that money to spend. I could probably only spend a couple of those dollars. So that's actually really what set the stage for my path to college, was this college fund that I had started and continued actually with all my sources of income. And I'll fast forward a little bit just because we don't have all afternoon, but I'll say in high school I really excelled in mathematics and really enjoyed the challenge of chemistry. I'm sure I must have taken a career, a Find Your Career program or a survey or something that said, hey, if you like math and you like chemistry, you might like chemical engineering. Really had no idea what chemical engineering was, but in faith, I stepped out and enrolled in school to take the prerequisites for chemical engineering. So I went to community college. While at Oakland Community College, I worked as an orthodontic assistant during the day and as a gymnastics instructor at night. And all of the other times speckled all throughout the rest, I took a full course load year-round. And upon completion of all of the undergrad, or all of the general requirements in the electives, I then decided it was time to transfer to Michigan State. So, at Michigan State University, I really hit some roadblocks. Up until that point, I'd been sufficiently challenged, worked very hard, but the chemical engineering program was tough for me, incredibly tough, in fact, and I had to work much harder, it seemed, than everyone else around me. I had regularly scheduled all-nighters. It sounds ridiculous, but in order to get all of my studying and all of the coursework done, I scheduled regular all-nighters. I'm not sure if that really paid off in the end, but I was able to make it through, and actually enough so much that I received a scholarship for my last 2 years. It was a full tuition scholarship, and at that point, I wasn't required to have to work a full workload so that I could focus on my studies a little bit more. So grateful for that scholarship. Now, while at Michigan State, I participated in internships, and I think that it's incredibly important, and it was really an invaluable aspect of my career path, for sure. My first internship was at AutoWiSE. It's an automotive safety device and restraint research and development facility. So, at this facility in Auburn Hills, Michigan, they actually performed the crash tests that perhaps you may have seen a commercial, the crash test dummies in their suits, and they had the long test track, and you could see the car crashes collide. And I was also able to see the development of the airbag, and the inflation of the airbag slows down to 1/10,000th of a second to show how differently the airbag, or unevenly the airbag inflates. And I was able to witness stress tests on the steering wheel, how much pressure and force of an accident or of a car or of a rollover can the steering wheel take before braking, and what was the flow during the manufacturing fabrication of the steering wheel. It was just really phenomenal work going on there. And my work there was much less glorified. I worked with spreadsheets. I automated, using Visual Basic, automated the population of spreadsheets. So my work didn't have anything to do with chemical engineering, but it really allowed me to see what a manufacturing research development facility was like, and it was a really fascinating world. You can develop connections, and it was just a truly invaluable experience for me. Another internship that I participated in one summer, I had been selected for an undergraduate research experience, and at Michigan State, I worked in the chemical engineering laboratory on the work of was called ammonia fiber explosion. So what that was actually was the use of biomass conversion. So the use of biomass as an alternate fuel source certainly isn't novel and wasn't then. But trying to get more from less, trying to get more energy from that same amount of mass. It seemed that there was some energy that could have been capitalized on that was just left over after the conversion of the biomass to a fuel source. And so my research experience was on the pre-treatment of biomass, such as corn stover and wheatgrass, switchgrass. So what we would do is, over a lot of temperatures and pressures, a huge test matrix, we would treat this biomass with a certain percentage of water. We would load it into this benchtop reactor, clamp it down, because then we would turn up the pressure inside the reactor to hundreds of psi. Instantly, we would turn the valve and depressurize, let the pressure go back. And upon depressurization, there was an explosion, so to speak. It was a very, very loud, acoustic sounding explosion that took place upon repressurization. And what that actually did is that much impact took the materials, took the cellulosic fiber, and it almost opened it up. It broke it open. So now there is all of the remaining parts that prior could not have been utilized could now be utilized for treatment for biomass. So it was essentially optimizing a process that really had already been in place. And I was able to do that throughout the summer, and in fact continue on through the school year, working in the laboratory, collecting samples, just monitoring the process, keeping the matrix, the test matrix organized, and it was a really, truly great experience. Now, this was entirely different than the research in a huge manufacturing facility. Here I was in a little lab, very little, in fact, a little bench top, and so it was just, I was able to see the research in academia as opposed to out in the commercial research world. So those are two of my internship experiences, and I then graduated from Michigan State University. Like I said, it was incredibly tough. It was a challenge for me, and so when I graduated and walked out those doors, I knew I was never going to look back, and I just felt like I needed to move forward. Apparently, academics weren't really for me, and so, but I graduated, and I landed my first job just before graduating I had a job offer with Accenture in Washington, D.C. So I moved to Washington, D.C. and participated in the training for consulting. It was a really, really fun job, and I don't know if that's really the best way to start a description of a job out, but it really was an incredibly fun job. The company flew me all around the country to go and make process improvements in other companies. It was a great experience. Unfortunately, I wasn't doing any of the technical work. Now, here I had busted my bottom trying to get through school, and I just was not feeling like this job was really gratifying. All that work that I put into the chemical engineering degree, and I wasn't using it at all. It was a very fun job, so I really found myself torn. I did start shortly after this job. I started looking for another job, and I found it was not a good time to be looking for a job. All of the requisitions that appeared were wanting 5 to 10 years experience or a graduate degree, and I hadn't either of those. I was newly out of undergrad. So here I am faced with participating in a job that really wasn't as gratifying for me. It was very fun, and the money was great, but I just did not feel like it satisfied all of that work that I had invested. So I find myself thinking, what do I do? Never saw it coming, never once. I started to look into grad school. I didn't even know who I was at that point because I must not have really been that happy, because I knew I was never going to go back, and here I am considering grad school again. And sure enough, I applied to Florida Tech and received a wonderful scholarship, and I just couldn't turn it down. It's Florida and Melbourne and all of the research and the Space Coast, and it just was a wonderful opportunity. But it's cool, and I found myself really torn. I did make the decision to go back to school because I truly did want something more. I want something that was worthy of all that I had invested. So I enrolled for the master's program at Florida Institute of Technology. I completed all of the required coursework and started looking for a job. I knew I wanted to have a job lined up by the time I finished my degree, and was incredibly blessed with a job at ENSCOPE. A professor from Florida Tech had sent an email out simply stating that one of his past coworkers was looking for someone for this particular role, and I was very anxious to get back out into the workforce after completing all of my coursework, and so I applied and was provided an offer at ENSCO as a chemical engineer, and I worked there for several years, and it was only a couple of years ago, in fact, that I ended up finishing the thesis aspect of the undergraduate degree, of the master's program. So I completed all of the coursework, but it wasn't until years later, many years later, that I actually finished the thesis. But there's no way I wasn't going to after all of the work I had invested in it. So now I'd like to share with you, now that I've shared with you how I got to where I am today, I'd just like to share a couple of areas of my work with you, to give a feel for some of the things that I'm involved in. One area, and the primary area, has been in emissions modeling. So, in this picture represented here is a chemical industrial facility, a chemical production facility. So we have reactors and distillation columns, and pumps and generators and storage tanks, and all of this could be the production of one or multiple chemical products. And so my role was to help identify, my current role is to look into well, what kind of emissions would I be expecting from a facility like this? So you see this tall stack here. You perhaps have seen them. I thought that they were cloud generators growing up, the white puffy clouds. I thought that they made those. And now I actually get to do research in what is going on, what's the phenomena that is actually making these clouds that you see. And also there is emissions that maybe aren't as obvious. For example, emissions from some of the storage tanks. So throughout the day, with the diurnal meteorological changes, temperatures, pressures, the various changes, the sun setting, rising, the chemicals within a storage container will expand and contract. So it will breathe, it will expand and contract as it heats up and cools down. The pressure rises and lowers. And in doing so, there's little teeny bits of chemicals that are emitted from these storage tanks. So one area of my work is looking at and modeling what kind of emissions would you expect from storage tanks. And another area is a lot of these units of chemical equipment are connected by piping running the whole line of this facility, perhaps from a feed to a reactor, from a product to an intermediate. And in that, you will have a lot of these pipes. And also, you have pumps and valves and flanges connecting one pipe to another, connecting one pipe to a reactor or to a valve or to a pump or compressor. And so the software that I work on is ENSCO, that was developed and I use operationally, in fact, is to identify the fugitive emissions that are coming from some of these valves, from the pumps, and from these flanges, so that we can have a really good picture of what kind of emissions we'll be expecting. Given a known chemical being produced, what kind of emissions would we expect as point source from the stack or from the fugitive emissions, or even some of the storage emissions, to see what chemicals are coming from this facility. And now, you may be wondering, well, now that you've produced this emission, what do you do with that? Well, I work with a multidisciplinary team of mathematicians and chemists, chemical engineers, meteorologists, to work on one entire system of the environmental transport of a chemical release into the environment. So, as I was discussing, my aspect has been producing the emission, the source term that starts off this domino effect. And then you will have that chemical being transported in a plume, and the meteorologists use their models to carry this plume to see where is this actually going. And the chemists and mathematicians are identifying now when that cloud is traveling with these chemicals, what kind of activity is going on with those chemicals? Well, you have the original chemicals that had been released, and now you have chemicals that were in the background. So there's reactions taking place with the chemicals that were released and the chemicals in the background. You have radiation taking place, and that sets off a whole cascade of reactions then. And then the cloud will continue to travel and change, and the chemicals now are not the same ones that were released, not the same concentrations that were released. And then you will subsequently, it will fall out of the atmosphere in a wet form or dry form. And just recently, actually, I've been involved in modeling and trying to understand and evaluate what happens once it's deposited on the ground. It's a whole new world of chemical reactions going on with whatever was existing on the ground, and the moisture of the ground, and the soil type, whether it's clay and what percentage of composition it is, if it was going to get absorbed into the ground, or perhaps if rain will come and carry that somewhere, and even perhaps evaporate off the ground. So that's been an area that's just recently, within the last couple of months actually, that I've been able to be involved in and help develop what then happens. What is the fate once this is deposited on the ground? And another area that I've been very interested with is with ion mobility spectrometry. It's an analytical method for detecting chemicals. Now, it has numerous applications, laboratory applications, and numerous applications, but most notably, and what I've been most interested in this technology for, has been for the detection of drugs and explosives and other toxic industrial chemicals. And so, how this works is the air will travel into this sampling device. This representation over on the left is really what's going on inside the detector in the upper right corner. And so it travels in through this detector, and each chemical is going to travel differently. And according to how it travels, when it goes through, there's a specific signature, a specific spectra that will be identified with particular constituents of a particular compound. And with that, the developers of these equipment will run numerous tons, hundreds, thousands of chemicals through the equipment to try to see what does this picture look like. And they produce a library of chlorine looks like this, RDX looks like this, by running numerous chemicals through to try to see what that structure looks like. Now, what does that actually do? What does that translate to? Well, then when the equipment is in the field, it will then know if it detects a particular chemical, it will run it against its whole library of chemicals to try to see what is this closest to. I'm seeing something, and oh, this picture that is presenting the spectra that I've created, that looks most like chlorine. So I'm going to alarm for chlorine, or I'm going to alarm for an organophosphate, or it will have numerous chemicals, and it will try to log against what it knows in its library. Well, these are used in military applications, at border patrol uses these. These are actually used at large events, the Olympics. They're located where they're trying to prevent any chemicals from getting, any unwanted chemicals from being involved in a certain region. And so they're also used in buildings. And now, one particular time that this equipment had been deployed in buildings, there was an alarm, and this was operational. This wasn't in the field test. This was operational. There was an alarm that took place in the government building in D.C., and it was Wednesday at 9 o'clock. Fortunately, most of the personnel had gone home for the day, but there still were some individuals remaining. They had to evacuate the personnel, and hazmat comes in their mock gear and tries to look for this. It's saying that there is a threat, a chemical threat that it has detected. And so they come in and they're looking for what's producing this alarm. They're not able to come up with anything. They don't find anything. Well, another Wednesday at 9 o'clock, the alarm goes off again. They have to follow protocol. They evacuate the individuals who are there. Hazmat team comes in and they're scouring the area, trying to identify that there is a chemical threat. They have to take every alarm seriously. It wasn't until this went on, finally, someone put together what was happening Wednesday at 9 o'clock in this facility. Oh, they were using floor stripper. They were cleaning the floors, and one of the chemicals in the floor stripper material it had a spectrum very similar to a chemical agent, and so it was alarming. It wasn't actually a harmful component that's temporarily in the air, but it wasn't truly a threat. So that said, there's a long way to go with some of the technology, with reducing some of the false alarms that are taking place, because things do often appear, that their spectra appears to be very similar. And so reducing the positive alarm, or the false positives and the false negatives, there's still a lot of research to be done, and that's one area that I've been able to take part in, is looking at the production of one of these, of a spectra, so of a picture of the chemical, but looking at it rather than from an experimental perspective, rather than doing tests over temperatures, pressures, rather than looking at it from an experimental perspective, looking at it from a theoretical perspective, using computational chemistry, and some of my coworkers can log into some of the largest, fastest supercomputers all over the United States to solve some of these very complex problems, the kinetics and dynamics associated with chemicals, and in an attempt to, from a first principles perspective, to try to map what this will actually look like, rather than from an experimental, try to reduce some of the false positive and false negative alarms. So that's another area that's just been fascinating for me to work in. I feel privileged just to be able to work with some of the individuals that I'm working with. And those are just two areas. Just due to time, I would love to share more with you, but decided to limit it to two areas for now. And I just wanted to provide some recommendations in conclusion. It wouldn't be a chemical engineering presentation without a mass balance. And in this case, my mass balance is money. I have to go back to the very beginning of my green little spreadsheet, bringing that back, and truly being able to say that I have no student loans now is just a feat. To know that this principle that was instilled in me it extends the ability to go to college. It's a truly long principle to adopt, and it's incredibly hard, but it's one that's just incredibly rewarding. So I have to say, paying for your own schooling is nothing can be more rewarding, nothing can be more challenging and rewarding at the same time. And just to know the value that you've invested in that class and is just truly rewarding. You won't appreciate education unless you've really had to work for it. So also, I really highly recommend, if nothing else, to participate in internships. A little bit of a segue into, I think that there are some internships that are research experiences that are available, paid or unpaid, regardless. It just offers an invaluable perspective into what could a job look like. We actually had an intern with us a couple of years ago with our company, and it turns out he just wasn't thriving. He just wasn't motivated, and it turns out he didn't want a desk job. It was great that he had an internship, an opportunity. It wasn't a full commitment. He had an opportunity to really get a feel for what would it look like as a chemical engineer. He said he wanted to be out in the field. He didn't want a desk job. So nothing is better than really just getting a feel for what the workforce looks like, what a career field looks like, even if it's not in your specific area of expertise. It's just an invaluable perspective to help drive your career, whether it's a laboratory that you would like to work in a plant, at a desk, and so also take advantage of career fairs. I know the community offers career fairs. They're posted publicly often. I know the school offers career opportunities. Take advantage of those and interview. Don't miss an opportunity to interview. Even if you're not all that interested in a job, still interview. Nothing is better than gaining that experience and being able to feel comfortable in an interview. If you're uncomfortable, it will show, unfortunately. So interviews truly are a great experience. And I'd like to leave you with some other jobs and careers that you could participate in as a chemical engineer. I chose these for no specific reason. They're in no order, other than the fact that I have close friends from my academic years that are in each of these areas. So I can say I personally know someone who's gone on the distillation process. I have my good friend works as a brewmaster for Miller and as a chemical engineer. And so there's just an infinite number of jobs in fields that you can go into with chemical engineering. It truly is limitless, and in fact, it's not even just the tip of the iceberg. Just a couple of applications I just wanted to provide, just to leave you with, get you thinking, and I'm available for any further questions. I know I just breezed through so much of my experience and my job opportunities, and I'm open to any questions for any more details. And so I'd like to open the floor up for any questions.
Questions for Lindsay? Can you talk about how it is to work with a team?
Oh.
A team of different people.
That's a really good question. My entire work at ENSCO, actually my entire experience through schooling